Okay, up to this point we have talked about how to deal with Lewis structures. We talked about things that have charges. We talked about resonance structures, talking about things moving electrons around. We need to talk about things that violate the octet rule. There's basically three situations. The first two are pretty uncommon. The last one happens all the time. So let's start with the weirder ones first. The first one is the idea of free radicals. For any of you with anxiety, I guess I will apologize because this is probably going to be infuriating. This is what happens when, at the very beginning, when you're adding up your electrons. This is what happens if you get an odd number. So an odd number of valence electrons. I'm just going to do an example. There really isn't tricks to this. You just end up with a frustrating answer. Okay, so let's look at NO2. So nitrogen has 5 valence electrons. Oxygen has 2 times 6. I said it backwards, but they have 6 electrons and there's 2 of them. Okay, so that's 12 plus 5 would be 17 electrons. This is a clear sign that there's going to be a problem. And I told you at the very beginning of the Lewis structure video that if you get an odd number here, double check your math. So I'm actually going to physically do that, even though I know I picked this one to be an example. But oxygen has 6 times 2 would be 12. Nitrogen is 5, so that's 17. 17 is the correct number. We don't really change the rules. You just do this like normal. It's just not going to be a good answer. So nitrogen's the central atom. We have 2 oxygens. We give each of them their electrons first. They have their octets, so that's 2, 4, 6, 8, 10, 12, 14, 16. Now the next step, you guys, step 4 in the process, says to place any remaining electrons on the central atom. It's nauseating, I guess, I don't know. So this does not have an octet. The next rule is to check for octets. This has 2, 4, 5. So we can form a double bond. I'm just going to arbitrarily pick one of the sides. Doesn't matter, which means we should have resonance structures for this. That would give us 7. We can't form another double bond because that would give us more than 8, and we can't have more than 8 for nitrogen. Okay, so the answer for this is this. Okay, let's check our formal charges. Okay, this oxygen is 6 minus 4 minus 2 is 0. This nitrogen is 5 minus 1 minus 3 is plus 1. This oxygen is 6 minus 1 is negative 1. It does add up to 0. Okay. You can't fix it. That's just the answer. Okay. A bit of terminology here. If you ever have a molecule that is neutral, doesn't have any charges, but there's a positive and a negative, we actually saw this with some of the other previous ones. I just forgot to mention it. This is called a Zwitter ion. Terminology is not that important, but basically it's neutral with charges. Okay, so if all the charges cancel out, but there's still charges, it's called a Zwitter ion. Yeah, free radicals, they mostly exist in the upper atmosphere. They're pretty unstable molecules, and so they need, usually ultraviolet light hits these things and causes this to happen. It rips off one of the electrons and everything gets really mad. Okay? There's no fixing this. That's as good as it gets. Okay, the second option are incomplete octets. This one is super rare. It's pretty much boron is like the only thing that does this. So let's just try an example and see what we mean here. So BF3 is a compound, okay? Boron is in column 3, so it has 3 valence electrons. Fluorine is in column 7, so it has 7 valence electrons. So 24 electrons. We're noticing that 24 seems to be a pretty common number. We're also noticing it's even, so we don't have to worry about any of this stuff. Okay, so if you were going to draw this, boron is farther away from fluorine than fluorine, so central atom. Give all the outer atoms their electrons first. If you double check everything, that adds up to 24. Rule 4 in the process, I was kind of skipping ahead here. Rule 4 says to check for octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and this boron only has 2, 4, 6. So you would basically have 3 resonance structures. I'm only going to draw 1. But basically you would expect one of the fluorines to have a double bond. Oops, I should have taken one of those electrons off. Sorry. Now we need to check the formal charges. This is 7 minus 4 minus 2 is positive 1. This is 7 minus 6 minus 1 is 0. This is the exact same situation. And this is 3 minus 0 minus 4 is negative 1. So here's a problem as far as charges go. We said that things that have charges, the more electronegative it is, the better it is at having a negative charge. The more electropositive it is, the farther it is this way, the more likely it is to tolerate a positive charge. What we have is literally the most electronegative atom on the periodic table with a positive charge, and a very, very positive atom with a negative charge. This is extremely unhappy. But it turns out that this is the right answer, because this is 7 minus 6 minus 1 is 0, this is 0, this is 0, and this is 3 minus 0 minus 3 is 0. So despite not having an octet, this gives everything 0 charges. So this is the right answer, and that one's wrong. I will tell you that this doesn't happen very often at all. Boron, as far as I'm aware, is the only element that ever does this. So it's pretty unique, okay? So not a big deal, doesn't happen very often, but this explains why BF3 is a perfectly happy molecule, even though it doesn't look like it looks like it should try to do this. Okay. Okay, the third set are sometimes called expanded valence shells. They're a little weird. These are things that have more than an octet. And you may ask yourself, you may say to yourself, I didn't think that was possible. That's not what you told us to do. Okay. It turns out that anything in the second row, so lithium, beryllium through neon, so basically carbon, nitrogen, oxygen, the usual suspects, can only have up to 8 electrons because they only have an s and p orbital to work with. So that's 2 plus another 6 would be 8. Okay, but it turns out that anything in the third row or below can violate the octet rule. Technically, they technically has an empty d orbital and can hold up to 18. You'll never see anything above like 12, but it can hold up to 18. Okay, so for example, the usual suspects for this are like phosphorus and sulfur. These things, pretty much anytime you see something with phosphorus or sulfur in it, it's probably going to violate the octet rule. Not always, but you should be on the lookout for this. Okay, so for example, sulfur. Well, let's look at oxygen versus sulfur. Let's look at the orbital diagrams. So oxygen, this would be helium, 2s, and 2p. I'm going to leave them empty, but basically each of these boxes can hold 2, so this means 8 electrons. Okay. Actually, we'll put the arrows in. This is why it usually forms 2 bonds, is it's got space for 2 more electrons. That's why it also forms a -2 charge. It gives it a total of 8. Sulfur is the same thing, just down a row. We never draw this, but technically the d orbital is available for use. So we expect the same answer. Sulfur will would happily form a -2 charge, it would happily bond to two things, but it is entirely possible to shove way more electrons in there and actually have it have more than an octet. It's actually completely okay with that. So even though, when we learned this, it was 3s2, 3p6, and we stopped. This is the 3d. Anything in the third row or below has a d orbital available to it, even if there's nothing in it. So I honestly visualize this like an attic. It's like empty space that if you need to store stuff in there, you can. This is why things in the third row or above can violate the octet rule. But I will tell you, they will only violate the octet rule to get rid of charges, which is actually what we saw back here. This violates the octet rule to get rid of charges. So let's look at, a pretty normal looking example. I'll probably try a couple examples and see what we can do here. So sulfate, perfectly reasonable thing. You guys have learned this one before. Sulfur has 6 valence electrons, oxygen has 6 times 4. These would give us another 2. Okay, so 6 times 5, because there's now 5 of them, would be 30, plus another 2 would be 32 electrons. Both of these are fairly electronegative, but oxygen is closer to fluorine than sulfur. So sulfur is the central atom. Okay, 1, 2, 3, 4 oxygens. Put electrons on the outside first. And it's overall, everything, we've gotten 32 electrons, everything has an octet, everything looks great. Until we check the formal charges. This is 6 minus 6 minus 1 is -1. This is -1, -1, -1, and this is 6 minus 0 minus 4 is +2. That is a ridiculous amount of charges. And yes, it has to add up to -2, and it does add up to -2, but this is still a stupid amount of charges. So what we find is that if we form double bonds, sulfur would actually get rid of charges. So if we formed 2 double bonds, like this has a +2 charge, forming a double bond here, or any of them, would get rid of one of those. Forming another double bond would get rid of another. So what we end up with is 2 double bonds. And if we check this, everything's still got an octet except for sulfur. Sulfur now has 2, 4, 6, 8, 10, 12, but sulfur is in the third row, so there's no problem. Okay? Essentially just starts shoving electrons in the d orbital because it can. This would be -1, this one would be -1. This is now 0 and 0, and this is 6 minus 6, 6 minus 0 minus 6 is 0. So it looked like it had an octet here, but we had a whole bunch of charges. Violating the octet rule will get rid of the charges, so it will do this. There would technically be 4 resonance structures because you could move the double bonds to all the possible options. I am not going to worry about that right now. Okay. Let's try one more. But technically it violated the octet rule, but it gets rid of the charges, so this is what sulfate looks like. Okay. There are some examples where you just don't really have a choice. This is a real compound, PCl5. So phosphorus is in column 5, chlorine is in column 7 times 5. So basically 40 electrons, if I counted right, I think. So phosphorus is the central atom because it's farther away from chlorine, and we need to attach 5 things to it, so we can't really use the right angle thing anymore. We're just going to shove 5 things on there. So before we even did any double bonds or had to do anything weird, this already violated the octet rule. It's got 2, 4, 6, 8, 10. Okay. Give the outer guys their electrons first. Okay. Now we check for octets. The chlorines all have octets. Phosphorus, giving it a double bond, it's only going to give it more electrons, but it has 10. It's violated the octet rule, but let's check the charges and see if it's okay. This is 7 minus 6 minus 1 is 0, so these are all 0. And this is 5 minus 0 minus 5. Everything's 0. This is a perfectly happy molecule, despite being really weird and ugly looking. Okay. Let's try one more. So, we said that the noble gases don't form compounds. It turns out that xenon and sometimes krypton under really harsh conditions can form compounds with oxygen and fluorine. This is a real molecule. So we still follow the same rules. Xenon is in column 8. This is 7 times 4. I don't know, 28 plus 8 would be 36, I hope. Hope my math works. Okay, xenon is our central atom. We have 4 fluorines attached. We give each of the outer ones their electrons first. We have used 2, 4, 6, 8 times 4 would be 32. We still have 4 electrons. The next rule in the little structure process says to place any remaining electrons in the central atom. We put them in lone pairs, so 1, 2, 3, 4. So this xenon has 2, 4, 6, 8, 10, 12 electrons around it. Let's check our charges. So this is 7 minus 6 minus 1 is 0. Those are all zeros. This is 8 minus 4 minus 4 is 0. Everything's happy, and it's violated the octet rule, but it's way down in the 5th row. It can handle more, anything that's not in the 2nd row, anything below it can handle more than 8. And it has 0 charge, so it's a happy molecule. Super weird, but certainly not impossible. Thanks.